Good afternoon, everyone. So, I think so far you have been hearing predominantly about AI and the way AI is helping different sectors. So, I'll be changing the tack a little bit and focusing on pushing your focus on a different aspect, which is related to how we can enable the rural economy and reach basically the capacity to that point. Otherwise, it's like we are building a lot of infrastructure, but ultimately it's about making it available to all equally. Uh, there a- on the table. That's right. Okay. Okay. So I'll just quickly switch over to the next. Yeah. So the need of the hour in terms of the capacity pipeline is to expand the number of base stations in different sectors and also actually have an extended capacity pipeline reaching those points. The reason why I'm emphasizing wireless backhaul here, I'll come to that point a little bit more, a little bit later. But the cell sites, when we went from 2G to 3G to 4G to now 5G and then 6G in the future, is that the number of cell sites are increasing dramatically. So if I have to elaborate that, when it was the 2G and 3G world, the cell sites used to be about a kilometer or a couple of kilometers apart. But when we went to 4G, the cell sites shrunk to almost like 400 meters. And in case of 5G, it is shrinking further. So it's like the capacity requirement is being met by increasing the cell sites and also increasing the capacity and also increasing the efficiency. So increasing the cell site is a very critical parameter. But when you start increasing the cell sites, you have to also think of how do we provide the capacity reaching to that cell site. So that's a very critical one. So the need of the hour is to actually have more and more cell sites, and 6G would be even more. It would come down to something called as nano and femto cells. So, but talking about all that, there is still one critical factor which we keep skipping out, which is what I want to highlight, which is if you look at the overall land mass, the population is very concentrated. So you have urban pockets where you have, let's say, very high density of population, and you have the rural areas which is very vast. But at the same time, if you look at the demographics, let's say India, the landmass being huge is almost like around 30 to 30 to 40% of the population is still residing in the rural sector. Only 60% is in the urban centers. So, but the area to cover is almost 1 is to 10. So there is an economic problem there, which makes it difficult for capacity to reach this 30 to 40% of the population. So if you look at the rural versus urban setting, if you install one tower in the urban setting, you would get hundreds of users. But if you go to a rural area, you will get only a few users. So that's why if you see the way the technology penetration happens, it's always in the urban centers predominantly, and in the rural areas, it will be always an afterthought. So one of the reasons why this also happens is because to lay the capacity reaching to all of this 1 is to 10, that ninth section or the 9 parts out of the 10 parts, you will need to lay a lot of fiber and reach to all of those corners. That makes it very, very expensive as a proposition and also not very effective to realize. And also it takes phenomenal time to deploy it. And also, especially when you start laying the fiber to reach the nook and corner, it becomes an unstable structure. People can just have fiber cuts and the outage will be significant, going in several days. So, the one of the predominant answers that at Astrome we have been finding out is to use a wireless backhaul mechanism to bridge the last mile. Now, when it comes to the last mile definition, I want to be very clear about it. It's like in Indian setting, for example, the BharatNet project has laid fiber reaching different gram panchayats to a scale of like, I think in India we have about 2.5 lakh gram panchayats. And they have tried to reach most of it. But that is not the end consuming point. From there, you need to still reach the final villages, which is almost 1:3, like 7.5 lakh villages. So to lay there, again, a fiber is a difficult proposition. And that's where a wireless technology like E-band frequency-based technology works very well. So E-band in particular is a frequency band which is in 71 to 76 gigahertz and 81 to 86 gigahertz for those of you who are not familiar with E-band. Uh, and here it has actually a tremendous large amount of bandwidth. Maybe I'll just spend a few seconds more to explain that. If you look at the 5G spectrum, for example, what is auctioned, they'll usually be in slices of 5 megahertz or 10 megahertz or 20, or in case of 28 gigahertz band, they will use something like 100, 120 megahertz or higher. But that's it. That is the maximum that is available. And that defines the final consumption capacity. Whereas here we are talking about a 10 gigahertz kind of bandwidth that is available. So that's a huge bandwidth that is available. And one of the reasons why E-band, despite its high capacity, has not been adopted for solving these kinds of last mile problem very effectively is because the existing ones have all mechanical antennas. You must have seen in every tower, there will be usually one round dish where it is basically a mechanical antenna which needs to be pointed very precisely to get the link. That actually adds to the deployment time, and also post deployment it adds to the maintenance cost, because any small misalignment it breaks the link and then you lose the network. So additionally, most of the E-band radios have had very short ranges. So it's like typically they talk about 1 kilometer to 3 kilometers. But if you look at the rural requirement, that spans to about 10 kilometers also. So you need some kind of disruption there which allows that. And that was basically a pointer for us. And we worked on it, and we have this product called as GigaMesh. This one we have now deployed in several rural settings and for long range settings with defense as well. Here, what we have essentially done is addressed those critical issues. The first issue being installation should be quick, where the entire alignment is purely driven by software and it is purely electronic. So there is no physical movement required for it to align. So it just stays there and it does the necessary electronic beamforming and beam steering and align the link, which is actually unheard of in E-band domain. So we are the first company in the world to do this. And additionally, we have also done something one level further, which is one E-band radio is able to create multiple simultaneous point-to-point links. So typically, if you have one tower and you want to link adjacent, say, 2 or 3 towers, you would need to put, let's say, one radio for each of the links. So that adds to the overall area and cost. Yeah, so I'll hurry up. Yeah, going further. So E-band, with our technology, we are able to do multiple links from one tower, which brings down the cost further. So yeah, going further, basically, all the advantages that I mentioned regarding range and multiple links is the primary selling point for us. And what we have seen is that as a future, the next step in terms of the evolution when we go to the 6G kind of domains is to integrate the system right from space as well. So the network will no longer be purely terrestrial play, but the space angle is an important angle which comes in. So we have already a product which is in the last stages of field testing called as GigaSat, which will actually link from the ground up. So that is being done for a specific customer, but it is being worked out for general LEO and MEO, which is the boom that is about to start. And also going further, we'll also be doing wireless links directly from space in the E-band frequencies. That's it. So thank you for listening to me. If there is anything specific, I'm available. I'm reachable. Thank you.